Hopefully everybody's okay. Good morning. Um, let's do a technical talk to start the morning off. But in this talk, first of all, everything you're going to see, there's a blog post with all the technical details. So now would be a good time to take a picture and then take a look at that later. The purpose of this talk is to maybe introduce you to two things. First, the idea of engineering and research teams working together. I've only been working in this style for the past couple of years, and I will share things that I've learned. I don't think a lot of engineers got to or exist today in that point, but let me just ask really quickly, how many people here in the organization have to coordinate or integrate with research teams in their company today? Okay, a little bit. Let's call it 1% of the people here. But I think that in the next few years, a lot of us will have to learn how to do it. So this talk should be interesting, especially if you've never done it before. And I'll introduce you to some of the issues that we have to work through. The second thing to introduce is Temporal, or Temporal, I don't know how to actually pronounce it, which is a workflow orchestration engine, and how we use it from a technical perspective to overcome some of the issues. A little bit about me. Yes, I wrote the book, The Art of Unit Testing, and I wrote a book called Elastic Leadership, and I currently work as a chief architect at Verbit.ai. A little bit about Verbit. It's a company that has AI running in production, not just in developer tools. So we do live transcription for media and legal cases, including finding inconsistencies with agentic workflows. It's pretty cool. And that requires a lot of work with both research and engineering. I'll tell you the biggest benefit of writing a book today, because nobody really reads books anymore. They just ask ChatGPT. However, most AI agents, AI models today have been trained on our books. I'm not sure if it's legally or illegally, but they've been trained on them. So now, whenever I open Cursor or any of the AI coding tools, I'll say, okay, review this in the style, or write test in the style of Roy Osherove's Art of Unit Testing, readable, maintainable, and it already knows what I'm talking about. So I don't need to add more context. It's actually trained on the book. So I highly recommend, if you want pre-trained models based on stuff that you care about, write a book about it, and probably 3 months later, it's going to be a model that has been trained on your book. Congratulations, you're now contributing to the models. Another recommended prompt, if you're trying these things and you want to do refactoring legacy code, is ask it to help you plan based on the book Working Effectively with Legacy Code by Michael Feathers. You're going to get a 10x IQ jump from the model just by asking these prompts. So if you've never tried adding books to your prompts with names, try it. You might be surprised. And with that, I'll get that out of the way. Our agenda is to talk about what does the day in the life of a researcher that has to work with developers look like, what the problems are, how we designed the solution, what it actually accomplished, and what it looks like after. I will start by explaining the complexity that we're all slowly facing in companies, whether just developing with AI or developing products that are based on AI as well. This is just a snapshot of some of the tools that we use today at our company, and I had to map that out. I'll give you a quick glimpse of what it looks like. At the top level, we have day-to-day chat models, like Claude, OpenAI, basically used for a lot of generic things throughout the company. Then we have development-centric coding tools, your cursors, your CLIs, Claude Code, etc. Then we have background coding agents, and those agents are the GitHub Copilot, etc., etc. Then we have research-centric AI tooling, like ClearML for deploying models and evaluations, and using the different platforms and consoles that the AI tools are using. And then production-facing, we have AI gateways that consolidate all of the configuration so that we can control tokens, routing, security. We have AI guardrails to control security. We have prompt management and monitoring tools. We have agentic frameworks like Crew AI, Claude Code SDK, etc. And then we have actual models being served, whether self-hosted or third-party managed. All these things, they contribute to this, I think somebody said burnout or being overcome with so much complexity, etc. And we're all kind of riding this wave of all these new tooling and technology. And in that wave, we're so focused on the tooling and technology, we're just running and we're trying it around like headless chickens. One of the things that we're starting, or we have to start formalizing, or important processes and patterns in this crazy world. So everybody's talking about the tools and tech. I'm going to talk about processes and patterns and a bit of technology in between and how it solved that problem. So here's one problem that exists in this type of organization, is that we have research teams creating machine learning algorithms. Now, these are not your standard algorithms that run in real time and do something, from your computer science class. These are multi-step workflows or pipelines that can take seconds to minutes to sometimes even hours. And I'll explain what that looks like when you work in a company like that. So imagine an application that has multiple pieces running, multiple services, etc. And these services have to use one of these ML algorithms. So imagine that we have inputs from customers that could be audio files, could be documents, and we have to somehow process specific types of files, specific types of audio, and then come out at the other end. Let me know if this is too high. And come out on the other end with something in the application that can be queried, or that it actually creates extra results in the UI for the customer. So these things are usually handled or designed by the research team and continuously optimized and somehow have to be used in our application. So engineers might be able to write some of it, but a lot of this work, a lot of the algorithmic work of optimizing not just prompts, but choosing the right models and processing and the different steps, that's up to the research team. So here's an example of a step. It's kind of a fake step, but it touches some of the production issues. Speaker voice indexing for future querying. So in this type of small pipeline, which is our ML algorithm, we'll take some file from S3 or multiple files. We'll take some configuration. We'll parse the configuration. We'll extract embeddings, which is basically a way to map out different things into an embedding model so we can query it later in a vector database. We'll do validation on some of the embeddings. We'll do reduction and a bunch of other steps that are not written here. But there's a bunch of steps, and each one depends on the other, and then save to a database like the new mappings, etc. And now we have something, a feature in the product we can use for voice indexing. This entire thing is designed and controlled by the research team and somehow has to be integrated into our application. So that's the beginning. Now, what does it look like from a researcher point of view, as I've found out in the past couple of years? Well, researchers, they start out with local playgrounds. There are different notebooks, or they have their own GitHub repository, and they'll do requirements discovery, and they'll create a data contract, which is basically what are the inputs and outputs that my ML algorithm requires. What does it expect? What does it need to deliver? They'll use metrics and evaluations to make sure that it actually works, and they'll create a baseline solution. What's a baseline solution? That's your alpha or your beta proof of concept, something that kind of works and it's somewhat usable and proves the point that this thing actually has viability. And then once it works and we integrate it into production, there is continuous iterative improvement. That's where a lot of the problems exist. Because now, imagine that they work in their own little playground, in their own GitHub repo, and they've come up with a solution. But the solution is written in a completely separate way. I wouldn't say it's vibe coded because they're not vibe coding things, but it is vibe researched in a way that they can continuously iterate They can do a lot of throwaway code, but eventually they'll get to the right set of steps that makes sense and actually produces the right result. Now they have to take this entire piece of code and somehow integrate it into a running production application. We all know that there's a difference about writing code versus making it production ready, right? So it has to be resilient, it has to be reliable, it has to be performant, it has to be readable, maintainable, all of that stuff. So if we're going to ask researchers to start integrating the code, which is how we started, you can imagine how frustrating that might be, because now researchers have to, let's say, integrate this so a service can call this algorithm. They can't use the code that they already wrote. They have to rewrite it, re-implement it in the structure of the new repository. So they have to know the structure, they have to know the design, they have to write the code in a good way, in a reliable way. And of course, the engineers working on the service also have to integrate, verify, test. They probably don't have tests for it, so we have to write tests for that stuff. Monitor it. So there is a lot of friction. And when I say a lot, I mean a lot. It takes 2 to 4 weeks to integrate a new algorithm into a service, just because of all the testing and back and forth involved, learning, testing, initializing. We're not even talking about what happens when it already runs in production. Now you have a new version of the algorithm. Now you have to reintegrate the new version. You have to go through that all over again. What if the structure changed? What if we find out in production there's an issue with the algorithm and we have to go and recreate it in the researcher playground? Like that back and forth becomes very frustrating. Of course, that's not even the hardest part. The hardest part is that in our application, in many applications today, they're distributed, they're event-based, so there's multiple services running. And the algorithm has to connect to multiple services in different parts of the life cycle to integrate different steps. And so what happens is that instead of integrating into a single repository, our poor researcher has to actually integrate into multiple repositories. So it takes even longer, and each repository has its own structure, its own set of rules, different developers that have to integrate. And that's where a lot of that frustration happens. Because researchers, at least the ones that I got to know so far, they really love doing the research part, and they're really not, they didn't sign up for doing the left part. There are people who signed up for doing the left part. Those are called, you know, MLOps or ML engineers. There's like the people in the middle. We'll talk about them in a second. So what's the other option? What if we don't ask researchers to do the integration? We'll ask the developers of the application to do the integration. So now we have knowledge transfer that has to happen from right to left, and we have oversight, support, and issue handling from right to left. And now the app engineers, which are not researchers by nature, they don't know how the algorithm is supposed to work, they just work on it from a surface level, they now have to somehow integrate this new algorithm and put it in the application, which adds a lot of overhead because they have to learn everything about the algorithm. And of course, testing it and all that stuff requires a lot of mentoring from the researchers. So their time is still very much occupied. ML engineers, if you've heard that term, or sometimes they're called applied scientists or applied researchers, they kind of live on that space in between where they live in the research world and they also live in the engineering world. So they know both realms, and their job usually is to get the knowledge of the researched algorithm and then integrate it. They're not pure developers. They're researchers who are also developers, or the developers that are also researchers. Now, this requires two things. First, it requires you to create a new role in your company. And you have to hire for that role, and you have to get that person in. And the second is that there is talk from different ML engineers is that that's not what they really love to do, is that if they come from the research world, they love doing also the research, but they usually get left with just integrating the results of the research. And so they're left with kind of a surface level integration And sometimes that can be very frustrating. But this role today exists almost as a glue between these different parts. And no matter which of these roads we choose, we always have this issue, is that there is a research playground where the research happens, and that code is not reusable in the production code. So if we find an issue in production, we have to go back and try to retry it in playground. If there's a playground issue, we have to re-implement it or iteratively reintegrate it into production code. And that is one of the most common pains today when you have development teams and research teams. And different companies are trying to solve it in different ways. Some companies are forcing researchers to basically work as part of the dev team and basically turn them into ML engineers, kind of generalists. And other companies are trying to work in different ways, like with ML engineers. We try to do a different thing. So how did we try to solve it? So now we have a task. We want to make it faster to integrate a new change from research. We want research to be able to iterate fast, but we don't want engineering to suffer on fast iterations. We want it to be less error-prone whenever we do the integration. Because imagine research integrating something that was written in one way to be implemented in a different way. Could be a lot of errors in that way. And we want to minimize the amount of dependencies. So we don't want researchers to wait for engineering to be able to integrate, and the other way around for iteration. Challenge accepted and received. So let's talk from an architect's point of view. How do we usually take a problem and we separate it so that we have a separation of concerns between problems? Well, one of the best ways is to abstract it away. And when we have a problem that's related to a long-running or not a real-time process, like an algorithm, what if we expose this algorithm as an API? What if we created a microservice per algorithm that you can just call the API, and it basically abstracts away our steps, our pipeline, and then the application just calls an API. So first of all, we separate the pieces of code. We all agree that that's good. But now we have a new problem. Now we have a new code base, a new service that we have to maintain, and we have all of the issues we had before. It has to be durable, maintainable, performant, scalable, all of that good stuff. So we didn't actually solve our problem completely. We still have all of the issues of rewriting the algorithm in a way that's production ready. Now, during that time when we were looking at solving this problem, we were also integrating another tool to our company, and that tool is called Temporal. We originally started using Temporal for different types of work. Temporal was used and is used as a workflow orchestration engine. And what we did is we took the same idea and we implemented temporal workflows for research tasks as well. So we co-opted what Temporal does and we applied it to research algorithms. And I'll explain what it is, but first let me explain what Temporal is. Has anyone here ever worked with Airflow or Dagster or Prefect? Okay, that's 2 people, that's amazing. N8N or something like that, cool. So you've heard of these things probably, at least N8N or a lot of the... Actually, you know what? Let me ask you this. Has anyone here ever worked with Circle CI, TeamCity, or any of the build to GitHub Actions? Those are also workflow orchestrators. Technically, they're a set of steps, with dependencies between them, and actions that can happen, and they do long-running actions. I guess you could co-opt one of them as well and turn it into this thing. But can you imagine having Circle CI running in production, running production algorithm from research? It's a bit of a problem. So Temporal is trying to solve the problem of these production scalable workflows that are designed to be scalable and durable. So it can do everything that the other things can do, but it's specifically designed for production use cases. So its main benefits are that no matter what happens, if everything goes down, let's say I know it never happens, but let's say that US East 1 on AWS goes down. I'm sure that never happened to anyone here in the past couple of months, right? Okay, got it. Okay, let's say it happens every couple of months. Every workflow that got dropped and is running and rerun will continue exactly where it left off. Even if you have multiple region drops on AWS, your workflows will continue to run. They're completely durable. I'll explain how that works. We can scale them to handle basically any amount of work, and they can take anywhere from a second to multiple years. So workflows are very durable. It's an open source platform that also has a managed version, and specifically designed to be this kind of durable platform that you deploy. You write code in any of your favorite programming languages. In our case, it's Python, but I'm going to show examples in TypeScript. The code runs in our environment because let's say that we're HIPAA compliant, we can run that code in our environment. It abstracts away the complexities related to distributed applications. What are some of the complexities? If I'm downloading files from S3, I might have a timeout issue, there might be a latency issue, there might be retries needed. If I'm sending calls to an API that is currently not available, I might need to do the retries. If I want to save state across multiple steps, instead of having multiple Lambda functions save state to an external database, I can manage that with these workflows, and I don't have to write the code for it. So basically, it gives us this abstraction layer that turns our logical code into durable code without writing 80 lines of code. We've all written these lines of code. Okay, do the retry, try catch, do this with back off coefficients to retry something. So it's great for these things. It's fault tolerant. So basically, no matter what happens, your worker, your code, your region falls down, it can be fully replayable from where it left off. So if we need resilient workflows that actually finish no matter what happens, eventually, this is a good way to do it. And again, they have SDKs for most of the popular programming environments. This is what it looks like when you run a workflow. It has its own UI. You can host it locally on your machine. Let me explain a little bit of what this workflow looks like. At the top, that's the entire workflow. Like this big green line is our entire workflow. And every step here is an example of what we'll call an activity. You can see that these activities, we're reading it from left to right, by the way. Each of these activities actually ran in parallel to each other. These ran in parallel to each other. This activity, you see that it has like this light green. It means that it actually retried a couple of times. And this one only started when this one finished. And we have the inputs, which are JSON. We have the results, which are JSON. And we have all of the information. And if we click on each activity, we can see the entire traceability of that activity. So imagine that you have this complicated workflow and you've coded it in just a couple of files, this entire thing. And this entire thing is fully production ready without asking people to write all that complicated code. Let me explain how Temporal works so I can explain how research and dev actually connect with each other. Temporal is based on workflows. That's like the big thing. And then it has activities. These are the steps that you saw running. It has workers, which are processes that you host. Think of it like a VM or a container that you host in your own VPC. And it has task queues. So a worker can listen to one or more queues with names. So I can send a bunch of work to multiple workers or to a single worker or to specific types of workers. And these workers will run the workflows for me. And then there's the Temporal server, which is either cloud or self-hosted. Now, the important thing to realize is that under the temporal level, all of the state of the workflows at each point and every activity is saved in the temporal server. And all of the workflows activities are stateless in that they can be replayed and recreated no matter what, because if they stop in the middle, the temporal cloud or the server will tell them where they finished and left off, and actually will give them all of the information needed to recreate the current state. It's like a mini blockchain, if you will, where all of the actions have been written down, and if you finished in the middle of this task right here, you will get to that exact point with these exact values and continue right from there when the worker goes up again. That's very powerful because that code is really complicated to get going and write. So the concept of workflows is that they have to be deterministic. And in our scenario, the people who write the workflows are the application engineers. They're in charge of the workflow at the top level. And the activities, which are the steps that we saw here, these are written and maintained by the researchers. So imagine that the activities are like these Lego bricks, reusable functions like Lego, that can be put in and imported into a workflow that calls them in a specific way. Research is responsible for writing all these steps, which are pure logic. And the steps that download stuff from S3, etc., developers can help write it, but it's reusable functions, basically, right, to download something. The big difference between activities and workflows is that workflows are deterministic. They cannot change state for anything else. The only thing that changes state are activities. If you want to call an API, use an activity to do it. If you want to download from S3, use an activity to do it. If you want to calculate something, you can do it in an activity. The workflow contains pure logic of just calling things in the right order and sending in the right inputs and getting the right outputs from these different things. And that is one of the design philosophies that we have to watch out for with Temporal. Once we pay attention to this stuff, we can get really, really far. So an activity that saves something to S3, if you retry it multiple times with the same file, it should end up with just a single file. So we have to write it in that way. That's what we call safe to retry. But the workflow doesn't have to do the retry mechanism. You just declare it. So what does this algorithm look like in Temporal? This is what it looks like. This is a slightly different algorithm, as you can see. You see that there's green and orange here. This is an example of multiple retries that eventually succeeded. And you can see the inputs, which are JSON inputs, and the outputs, which is the result of the continuous workflow, and how long it took, who triggered it, etc. In Python, this is how we would write the workflow. So you literally create a class and you put a decorator on top of it. And in this workflow, using the SDK, you call execute activity, and you call an activity called speaker identification. And you just say start to close timeout is this, retry mechanism is this, etc. Just a couple of lines of code. This is what an activity looks like in Python. Let's say it just returns the concatenation of a string. It's literally just a function with an attribute on it, with a decorator. So you can take the functions that were created by research and just wrap them in these activity definitions. Let me show you a quick demo. This is an empty workflow temporal server that I have running. And this is an example of a simple workflow that shows exactly what I just showed you in the screenshot. So this is a research workflow, as an example that I wrote. It's written in TypeScript. And in this case, you'll see that it literally calls these functions. Let's say load file from S3, load JSON config, prepare config, extract embeddings, validate, all these things. These are the activities themselves being imported. Okay? This is the output of the entire workflow. So this entire workflow are these lines of code. Everything else is just imports and interfaces. Okay? And these are different activities that we can configure with timeouts, retry mechanisms. You see the load from S3. So these activities, let's say reduce embeddings, are just TypeScript functions. And I created them as samples, so they just take fake time, and they might actually need to retry sometimes, just so you can see what it looks like. Save to DB, take some time, What else? Oh, here. I created a function called validate embeddings that will just check how many attempts and only work on the third attempt, just so you can see what it looks like. But notice that there is nothing special here in these logical functions. We don't have to worry about all of the mechanisms around them, the retriability and the output. So I already have a temporal server running here with a command line, and I have a worker running. This is what the worker looks like. The worker is just a process that connects to our running temporal server and starts listening on gRPC. That's it. So this is the entire worker. You can put it in a container, run multiple workers on Kubernetes or anything you want to do. So we have workflows, we have activities. Now I'm just going to do run workflow, which is literally just calling the API of Temporal and triggering the workflow. So in this client, you can see that I'm just using the SDK, and I trigger the workflow with a specific task queue, and I send in some input. So I'm just going to run this for a second, and this will run the workflow. So I'm going to refresh this. You can see a one workflow running, and this is what it looks like in real time as the workflows are starting. So you can track production workflows running in your application, and remember that each one of these activities can actually call a completely different system in your product. You can do multi-system calls, but they're all, the state across these is saved in the workflow itself. So now I can do really complicated stuff. Let's say a user gets created. Okay, create credentials for that user in this one system. Create an order for that user in this other. Charge that user in the third system. If it's not charged, reverse the charges. All these things exist in this one thing. So I can click, for example, on this activity. I can see the inputs for it. I can see the result that it created. I can click on this activity, and I can see the errors, and I can see the final result. This is the input, and I can see the final result that it created. It doesn't really matter what it created, it just matters that I can trace it. And of course, this entire thing runs in a worker that I can control. So now we have full traceability across our entire life cycle for something that can be really, really complicated to implement as a cross system. Now, this could be a research-related algorithm, or it could just be one of our features. We use it for both. Okay, so when we deploy a worker, that's just that code. We deploy it, in our case, to AWS, and we have multiple workers. Usually, different teams and domains will have different workers that they run because they might have different requirements for the worker, like higher, sometimes GPU, sometimes CPU, sometimes different memory, sometimes multiple workers on the same queue, depending on the types of workflows. The workers are talking to Temporal Cloud using gRPC. Temporal Cloud listens to the queues, and our applications trigger an API call using calling a temporal queue. So our applications don't actually call the workers directly. They always call it through the temporal server. Temporal server takes care of the reliability and all of the other aspects of it. We also have an event-based system, so we actually also have an event bridge listener, a router Lambda, that will trigger the API, so different systems can connect to event bridge. So what does it look like in real life? Well, in real life, how do we do this integration? The researchers have their repository. Remember that repository we talked about? This is the pure logic repository. And then they have one extra repository on top of it, which is the domain and the activities stable. All that are just wrappers, simple functions that call the underlying logic. And they have that activity definition on top of them. That's the entire thing that researchers are doing. Engineers on the application they have a separate repository that runs the workflows. So at the beginning, we designed the workflow along with research, but once the workflow gets created and just runs the activities, all it does is just imports the activities from that other repository, which basically means that once we have a workflow up and running in production, it's a fire and forget situation. This is our handoff line. We call it zero-touch integration. So researchers can continuously iterate and push new changes to the repositories of the activities, and slowly iterate on the algorithm. As long as the data contracts, inputs and outputs don't change, they have continuous CI/CD, or continuous delivery for the algorithm, and developers and workflows automatically get the latest changes. So there's nothing to do from the app engineer side, and there's nothing to integrate from the researcher side other than working on these completely separate repositories, which means that there's much less frustration going on. So what does it look like today versus yesterday? Well, if it took 2 to 4 weeks to implement one of these ML algorithms, today it takes less than a day once they get to the baseline solution. If we want to iterate on these changes, again, 1 to 2 weeks with all the tests, now it takes less than an hour. And it only takes one person to change these algorithms, which is our researcher. So this is that previous version that we saw before. Our researchers are doing all that stuff that they did before, and then they push new changes into the temporal activity repository. That stuff gets re-imported by the workflow. Developers don't have to do anything, researchers don't have to do anything else. And now we can do iterative improvement by just pushing these things. So here's an example of what it enables. One of the biggest problems is that when you have a new feature that you have to work on, developers need to come up with the feature and the POC of the feature as fast as possible, because you want to be fast in the market. Researchers usually work much slower. They have this iterative thing going on, which makes sense. So we want researchers to come up with the baseline solution as quickly as possible, just so we have a running workflow in production. And then they can continuously iterate. So no longer are they the bottleneck for developers to develop things into production. We determine the data contracts, we create a baseline, very simple algorithm, and then we just keep improving it. But the application is already running in production. So there's really, really fast iterative changes. The only time where we have to do reintegration and change the workflow is if we decide that we actually need more different types of activities, or the data contract and the inputs and outputs need to change. But that happens 20% of the time, and 80% of the time it doesn't happen. So far we're really, really happy with this type of change. This is another example from another temporal UI that runs for other different types of chunking strategies. And we can do a lot of really cool things in that we can change the throughput of the algorithms by changing the workflow configuration. So you can decide how many activities run in parallel, so you can reduce the amount of either tokens being used, or CPUs, or memory. But researchers don't have to do it. It's mostly done by the dev team. Okay, some thoughts about the future. One of the things that we recommend and we started doing in our workflows is splitting activities. It's at the beginning, one of the anti-patterns that happens is that researchers create this one big activity that does all the steps. And then we take this one activity and we call it from the workflow. So the entire workflow is just calling one activity that could take a long time. There's almost no visibility into what's going on. So one of the practices we're introducing is activity splitting, where the algorithm is designed, but it's also designed with activities in mind, so like Lego pieces. In this example, the chunk splitting activity is something that was split. And before that, in the previous version of this algorithm, the entire algorithm was just like three different activities. There's like configuration, do the thing, and then save the result. So there was like one huge activity that just took a long time with zero visibility, and we split it up and created like a sliding window that runs multiple activities in parallel. But that took time, and it requires research to also work with us. So it's not zero work if you want to redesign the algorithm and the steps, but it's something that's highly recommended. Split the activities into reusable, traceable chunks. The other thing is that configuration management for our workflows has to come in somewhere. So you either grab configuration from like a third party like S3, or you send it through the inputs to the workflow. And we are still learning how to best accomplish it, because different algorithms from research require different configurations for different use cases. So designing the data contract in advance sometimes is not good enough because we realize that we need more configuration in the future, and then we have to change the data contract again, and it requires more changes. The other option is to change configuration from like S3 or another database, requires again more integration. So we still haven't solved that stuff. Like how do we do continuous configuration management in different environments and with different types of algorithms? But we're slowly working on it. We want quicker feedback loop when the contracts have to change. Right now, if we change the inputs or the outputs to the workflow, we only find it out a bit too late, only when we deploy to specific environments. We want to do continuous integration and testing locally with fully automated workflows, and we're slowly getting there. The other thing that happens is you have dependencies. All these activities have dependencies on different versions and different things. So if you have one repository that the entire team is contributing activities to, different activities might need different versions of the same library. So you have this dependency hell that sometimes happens. So you have to start breaking it up, or we have to formalize. Still, again, sometimes a bit of a frustrating issue because you want to treat them like Lego bricks, but different Lego bricks have different dependencies, and you don't want to bring all the dependencies into your workflow. And we want to come up with a set of good practices in the future so that people can continue work with it effectively. If you want to find out more info, or if you want to see this, you can check it out on my blog at robotpaper.ai. Everything I just wrote here, including examples of code, is available there. I want to thank you, everybody, and may the force be with you. Thank you.